Okay, I really like problem number 11 here. It asks you something straightforward. We're supposed to compute the value of the definite integral from 0 to 10 of a linear function here, 8 minus x dx with respect to x in two different ways. One, as a limit as n approaches infinity of r sub n. That's interesting. And the second one is the more straightforward way using area and geometry. So I'm going to do this second one here first because I think this is a lot easier. So what we're doing here, guys, is we're looking at, let's take a look right here, a linear function, 8 minus x. So we're going to have a y-intercept up here of 8, that's where we're starting, and a slope of -1, which means we're going to take this down like this. And what I'm hoping you guys can tell me right now is that if our slope is -1, our x-intercept there is going to be 8. But you'll notice they want us to take this thing all the way to 10. So it's going to go a little bit further and end right here when we're at 10. And what did that do? That created two regions for us there, guys, that we're going to have to find the area of in order to evaluate this definite integral. So the area of region number 1, that's a triangle, and it's 1/2 times your base times your height. And I think this one's pretty easy to see. Your base there is going to be 8. Your height on the left is going to be 8 as well, and half of 64 is going to be 32. Then, for the area of region number 2, it's 1/2 times a base of, well, from 8 to 10, that's 2, and a height, that's going to be 2 as well. Half of 4 is 2. And therefore, the integral now from 0 to 10 of 8 minus x dx is going to equal this area here, which is above the x-axis, and here's what's important, minus now the area of any region below the x-axis. 32 minus 2, and we end up with an answer of 30. Now, remember, normally, what you guys are probably used to already is using an integral to find an area. But what we're doing right now, at least what we did in part B, is using an area to find an integral. Now, part A is by far the trickier part here. How are we supposed to evaluate a limit as n approaches infinity? Well, what I would probably do here, guys, is I would start off with a finite value of n that works pretty well for this particular interval from 0 to 10. I'll tell you what we're going to do first. We're going to do r sub 10. Okay, and this is where sigma notation really comes in handy, because doing this by hand would be a pain. All right, guys, what happens? Our overall width right here from 0 to 10 is 10, and when we divide that by 10, we're going to get a delta x value equal to 1. And then in brackets right here, we take the height of each one of our right endpoint rectangles. So, let me go back to my drawing here. My first rectangle, I'm going to shift colors here, we'll go purple. My first rectangle would probably look something like this, and a right endpoint rectangle would go up until it hits the curve, back left, and down. And there's rectangle number 1. That first subinterval starts at 0 and ends at 1. So the height of that rectangle is going to be f of 1. The second subinterval starts at 1 and ends at 2, so its height right there would be f of 2. And we'll keep going all the way until the last subinterval, which goes from 9 to 10, its height would be f of 10. Okay, so let me get this consistent now. Now, it would be doable, but kind of a pain, to put all that into my calculator that way, so let's do some sigmas. This is a 1 times a summation right here, and we're going to start now at k equals, well, this one's pretty straightforward, guys. At k equals 1, we're going to do 10 rectangles, and all that's going on here for the height of that each rectangle is going to be f of, now our delta x value we said here was going to be 1, so that's just going to be a 1k, and then usually you have to add or subtract something at the end, but not in this case. When you start with k equals 1, this becomes f of 1, which is exactly what we wanted. Then when k is 2, this is f of 2, got it? And last one, when k is 10, you end with f of 10. So this one was pretty straightforward. Now, This is going to take me a second to put in there. I've got to put the function into my calculator. Oh, sorry about that. Got to put the function into my calculator. So let me redefine what I had here before. So we're going to, no, not derivative. That's not what I meant. Got to go back a menu. Here we go. Actions, and then define. So this function, we're going to say f of x is equal to, this was an 8 minus x, and hit enter, and there we go. And so this sigma, guys, was a 1 times, and again now it's going to be menu, and for you guys, you're going to hit number 4 for calculus and number 5 for sum. I keep doing k, but for this I'm just going to do an r instead. And we started it now at r equals 1. We go up until we get to 10. And then the function here was going to be, all right, I forgot this last time. We'll do an f of, and we said it was going to be delta x, which was just 1, multiplied by r with nothing added at the end of all that. So I think that's what we had written out, and we came up with an answer of 25. So let me write that down real quick. All right, so 25 is our first answer right there, which you'll notice is in the ballpark here compared to what we believe is the real answer, which is 30. Furthermore, guys, if you look at those two purple rectangles that I've drawn, they're both missing area right here and right here, which makes sense then that this answer is below, less than, what we think is the real version right there. All right, guys, all we've done so far is r of 10. Now the plot thickens. Let's try r of 20. Now what's that going to do for us? The width of each rectangle is now half of what it was before. Previously our delta x was 1, 10 divided by 10. Now it's 10 divided by 20. So 1/2 is the width of each rectangle. By the way, I should say, guys, I've chosen two arbitrary values right here. You'll notice 20 is bigger than 10. You could have chosen different numbers, but I'm really going to get the payoff here on the third one that I'm about to do. Okay, then what happens in brackets here, guys? We're going to now take the height of 20 different rectangles, and the first one here is going to be f of, well, let's think about this. Now our first subinterval starts at 0 and ends not at 1, but at 1/2. And the right end point then is going to be that 1/2. And then we're adding this delta x value each step along the way. So plus f of 1 plus a dot, dot, dot. And we'll end that last subinterval, its right end point is still going to be 10. So f of 10, and there we go. Okay, so that's the setup here on paper, but I really don't want to type 20 of those into my calculator, so let's practice sigma notation. A 1/2 is going to get multiplied by a sigma, which we would start at, sure, we'll keep doing k equals 1, but this time, guys, with 20 rectangles, we have to put a 20 up here on top. And now, what comes next? The height of each rectangle is going to be f of. Now, you're always going to multiply your delta x, this value right here, by k. So this is going to be a 1/2 k. And now let's see if this one works. If I put in k equals 1, 1/2 times 1 is 1/2. I don't need to add or subtract anything right there. I think I got it. Let me check it when k is 2. Half of 2 is 1. F of 1 is what I wanted for my second term. And lastly, let's check it at 20. That should get me right here. 1/2 of 20 is 10, and that's the f of 10 that I wanted. So, okay, this one wasn't that bad. So I just need to change a couple of things from my previous expression right here. And is it worth? No, I'm just going to start fresh. Here we go. We have a 1/2 out in front. That's going to get multiplied by, and again, it's menu 45 for you guys. And we're doing, again, you had a K. I'm going to put an R, 1, and we stop it after we get to 20. And now for the function itself, it is going to be, we said f of, in parentheses, that was a 1/2 multiplied by, you guys had k, I'm going to put an r right there. And there we get 55 over 2, which is what, 27.5. So how do I feel about that answer here, guys? Well, again, it's in the ballpark between the 25 that we came up with previously and the 30 that we think is the final answer. In fact, it looks like it's getting closer to the right answer here of 30, which kind of makes some sense because the more I do this, the more rectangles that I have, the more accurate my answer should become. Okay, we're making some progress here, guys. There we go. And I think I'm going to do this one more time. And now I'm going to go with R. Let's see, I did R10, I did R20. Now we're not messing around. Now we're going R100. Let's do it. It's really no different, guys, than what we've done before. It's just a conceptual change. The width of each rectangle now is going to be what? It was B minus A, so that would be 10 minus 0 all over 100 now. 10 over 100, 1/10 is going to be the width of each rectangle. And then in brackets, here we go. The first subinterval is now going to go from 0 to 1/10. So we're going to begin this thing with an f of 1/10. The second rectangle, okay, goes from what, here we go, is going to go 1/10 beyond that. Okay, this one's going to go from 1/10 to 2/10. So that would be 1/5. I'll just leave that as 2/10 right there. Gotcha. And then a plus ... And the last rectangle is still going to have a height of f of 10. That is still going to be the right endpoint of that last subinterval. So where are we going with this? 1/10 multiplied by, and we're going to do a summation now. We'll start this again at k equals 1. We're doing 100 rectangles. So there's 100 up there on the top. And the function itself is going to be f of, you always multiply your delta x here times your k. So that's going to be a 1/10 k. And let's see if it works. The last two did. Put in a 1. 1/10 times 1 is 1/10, right where we want it to be. Let k equal 2. 1/10 times 2 is 2/10. The second one works. And the last one, let k be 100. 1/10 times 100 is 10, and you wanted to end that with f of 10. So I think we're in great shape here, guys. So let's try this again now. And I tell you what, this one I am going to just go back and edit what I did before. Up, up, enter. And let me hit my left arrow about a zillion times right now. And instead of a 1/2 now for the width of each rectangle, that was now going to become a 1/10. What else changes? We're still starting this. You guys said K, I said R equals 1. But up on top, that 20, we're now going up until we get to a 100. And then to the right now, instead of a 1/2 R, that we said was going to be a 1/10 R. So a 1/10, 1/10, and 100 on the top. I want to make sure I have that typed in right, and I think I do. Let's see what we get here now, guys. 59 over 2, which is going to be 29.5, if I'm not mistaken. 29.5. So where are we here, guys? 29.5. What I want you to do at this point is take a look at the three answers that we've come up with here. When we did 10 rectangles, we got an answer of 25. When we got 20 rectangles, we got an answer of 27.5. And when we increased up to 100 rectangles, we got an answer of 29.5. So the question here is, everybody, if we look at the pattern right here, I hope it's easy to see right here, that our right approximation values are going from 25 to 27.5 to 20.5. They are converging towards what value, guys? Looks like they're going to a value of 30, which of course matches the answer that we got using geometry like 15 minutes ago. So what do I want you guys to take from this big, ooh, that was ugly. What do I want you guys to take from this big, ugly problem here? If you can use area and geometry, that is much, much faster than trying to evaluate a limit right here as n is approaching infinity. But either way you do it, we end up with the same answer here of 30.